Yeah, I guess I'll start with the introduction. Yeah, good morning, everybody. It's my pleasure to introduce Mila Nikolova as our today's first speaker in the morning from ENS Cachan, and we're looking forward to a talk on below the surface of non-local Bayes.
Thank you for the introduction. This is a work we did with Pablo Arias, who is in my lab. The talk is about the non-local Bayes algorithm that was introduced by Marc Lebrun, Anthony Buades, and Jean-Michel Morel, and it is a state-of-the-art algorithm. And well, my goal will be to see what really happens and why this is successful, and we will see that the success of the algorithm is not due to the factors that were planned to do it successful. Something other happens in the algorithm. So now I have to switch to a video which is in another file. I could not make the compilation correctly. So how can I do this? File, view, read mode. This is the pipeline of the many denoising algorithms. The idea is to first denoise the patches and then to aggregate them. So let me show. Given a noisy image, we extract n similar patches. We have a prior on the patches and we denoise them. In fact, we denoise groups of patches and then aggregate them. So with the red, in the red is a patch. It's a group of 5 pixels, and the nearest neighboring patches, the group of patches, are given by the green squares. So all these groups will be denoised in the same time. Oh, the video did not work. So you can see how it proceeds. Each time a red patch is chosen, the neighboring patches, sometimes they overlap. It depends on the image. And they are jointly denoised and then aggregated. By aggregation, I mean that the mean value is taken for each pixel that was already denoised. The mean value will be taken. In this stuff, we do not, in the denoising step, there is a special processing for the flat areas, but I will discuss about this later. Can I stop the video? So what happens next? This is the first step. methods use the same, very similar approach. They differ basically in the way how to denoise the patches. Different priors and different models are chosen, and then an aggregation step is applied. Usually this aggregation step is just one sentence somewhere in the paper. Sometimes it is just one word. The main difference is how to make the most performant denoising step for the patches. For instance, the famous BM3D algorithm, the 3D stacks of similar patches are supposed to be sparse in a transformed domain. There is a lot of research on the denoising how to find the best denoiser for the patches for the first step processing. And there is not so much, that there is no research about the second step, the aggregation. So in this talk we will show with something quite surprising that the disaggregation step plays a very crucial role for the success of the algorithm. Maybe not only this one, maybe all algorithms that make aggregation. I will illustrate this by some numerical tests. How this started, this topic? This is a statistical approach, very well Bayesian grounded. And Pablo gave a talk about, can we finally really find a unified approach and have a full Bayesian explanation of the thing? So we found something a little bit different that I will present now. First, I will present the algorithm in more details, and then I will say why it is successful and what really happens. So we have, as I mentioned, we extract n similar patches. We estimate, you have a prior which is very simple, Gaussian prior. We have the covariance matrix, estimate the mean and denoise by Wiener filtering and aggregate by average. Nothing special here. However, you see that when you come to the aggregation step, something happens. The image looks much nicer. At the second step, the first step, the image obtained after the aggregation in the first step is used as a guide. In fact, only the covariance of this matrix is used as a guide, and then we run it, the same approach is run again. I'll give the formula in a few minutes. Then, when we have the correct covariance matrix, we do the same and aggregate, and then aggregate by averaging. Let me show some close-ups. This is the noisy image, this is the original. This is the result of the first step of the algorithm, which consists of a denoising and an aggregation step, denoising of all patches and then aggregation, with the estimated covariance matrix. And here is the second step. We use the covariance matrix of this one, and we do the same Wiener filtering with the covariance matrix that we use as a guide from here. So you can observe that the first step, denoising, is the most of the work is done here, and that certainly there is an improvement, but it is the most of the improvement compared to the noise image is done in the first step of the algorithm. So we have, suppose that we have n similar clean patches from an image U that we want to estimate, but we have only n similar noisy patches Q1, Qn, and from the noisy image that we denote by V. The assumptions are very simple. Everything is Gaussian. The patches, all the family of similar patches, share the same mean and the same covariance matrix, and the noise and the image is corrupted by additive Gaussian noise with known variance. It is naturally it is assumed to be independent of the image. The Wiener filter, which is in fact the maximum a posteriori estimator, amounts to a Wiener filter. So to estimate, when we know the covariance matrix, it amounts to take the mean, subtract the mean from each patch. This is the filter, and this is the MIP estimator, or the output of the Wiener filter. We can decompose the covariance matrix in the SVD basis, singular. Here are the eigenvalues, and these are orthogonal matrices. And here we can see that there is a weighting. If we can consider equivalently that the denoising is for a group of patches, of similar patches, is done in the basis determined by this orthogonal matrix. And then we have the filtering coefficients, which are given by a diagonal matrix. They are given here. This is when we know the covariance matrix. This is what we do in the second step, which is just very, very classical. However, we do not know this covariance matrix. We do not know the mean of these neighboring patches. When we have only the noisy image, we know only the sigma. So in the old language we were saying we estimate them. Now we have to say we learn them. And so what we do is that we take the mean of all neighboring patches and compute the empirical covariance matrix. This is the estimated covariance matrix on the noisy patches, and we have to, in order to get an estimate of the covariance matrix of the true image, we have to subtract the noise, the covariance of the noise, which is just a diagonal matrix multiplied by sigma square. So we are given this equation. Here this is the estimated mean of the patches, and this is the whole expression. We have to subtract, I don't know if it is clear, in order to get the covariance of the true image. It is given by in fact, it is given by this sum. So we have to do this subtraction here. And what it can, in particular, we see that if we consider the orthogonal decomposition that I presented before, the weighting coefficients, the estimated eigenvalues of the covariance matrix are given by this expression. Let me mention what happens with the flat, for flat patches. There is a statistical test that determines whether or not a group of similar patches is flat. If the group of similar patches is flat, then the mean value of the whole group is assigned to all the pixels in this group of patches. You can see the group patches that are, this is the decomposition and this is the final result. These are represents the numbers of times each pixel was estimated by this group patch denoising, and you can see that some pixels were estimated much more times than other pixels. By flat patch, I mean a patch that is it is assumed to be constant. So let's go further. How to see the first step denoising? We write, we do not know this metric, so we estimate it in this way. This is the covariance matrix computed from the noisy data, and in order to have an estimate of the true covariance matrix, we have this expression, and we can make an orthogonal decomposition of the obtained covariance matrix, and it reads in this way. This is the empirical covariance matrix, and when we write it in this way, we see that the weights, the filter weights are given by this expression. In fact, it was believed that this should be always non-negative, but when you plot it, you see that it is unbounded, can be unbounded for small negative. Here the noise, the level of the noise is 20, so the sigma square, the variance, is 400. So you see that for eigenvalues that are smaller than 400, the empirical Wiener filter will have negative weights, and they can be very, very negative. This is an example from the image that I gave, the parrot image with noise with sigma equal 20. The patch size is 5 by 5. According to the rules, you have to choose 75 neighboring patches in a given region. Here are the eigenvectors 75 of this patch. The 75 eigenvectors are given in a lexicographical order. Is it clear what is the matrix hat UQ? Yes or not? This is this matrix. We can consider the denoising into this basis, in the basis of the singular variable decomposition of the empirical covariance matrix, and here these are the eigenvectors. Then they are weighted by these coefficients, weighting these filter weights. And the eigenvectors are given here. You can see that this one is the main, and the others are the closest one, but then they are not really very close. Here are the eigenvalues of the noisy data, of the covariance matrix of the noisy data. Most of them are smaller than 400 sigma square, and they will give rise to negative weighting coefficients. Some of them go up to -3, and what this means, that this patch will be multiplied by the number here, the second patch here will be multiplied by the second number, and when we go to patch number 5, 10, starting from this patch, this patch will be weighted by a negative weight, so which means that it will be reversed. All the pixels will take the opposite sign, and a weight which goes from minus something up to -3 for the last one. And we can also observe that the last rows of this image, the patches are basically non-informative, because they are basically noise. Visually they are noise, they are not very similar to the first patch. Usually when we make this decomposition, we would expect that the first few eigenvectors that are the most important will be weighted by some positive weight, and the other ones are just attenuated. This is not the case here. So what we did a theorem showing that there should be negative eigenvalues in the empirical covariance matrix, but finally we just computed them, and it was easier. So there are always negative eigenvalues in the empirical covariance matrix in the first step of the non-local bias denoising. Here is the minimum value of the weighting coefficients, in percentage. No, the minimum value. Here are the group of patches, the percentage of the group of patches that have at least one negative weight. It goes up to, you see, for sigma equal 1 there are 70%, and starting from 5 it is nearly 100. And the average percentage of negative weights per group of patches is also very important. These tests were done on 5 different images, and here we consider only non-flat areas, because flat areas have a special treatment, so to be clean it's better to use non-flat patches. What happens in the second step? Here is are again the eigenvectors of the decomposition in a lexicographical order. Here are the eigenvalues of the covariance matrix. It is about the same image, and the corresponding weights are given here. They are very reasonable. You see that the first few patches are quite reasonable, maybe 6 or 7 patches, and then the others are not very representative, and they are really attenuated as expected by the weighting, by the Wiener filter. Here is an example, again with the same parrot image, with the same patch size, the same neighborhood, the same noisy data. This is the covariance metric, the empirical covariance matrix. It does not look very nice. And this is the covariance matrix estimated after the aggregation in the first stage, the first step. It looks much more informative. And this is the covariance matrix that is used as a guide in the second step denoising. Well, here is what this was a kind of unexpected. This is the error of the noisy patches here, of the noisy patches. If you consider the error of the patches that were restored using the empirical Wiener filter before the aggregation, you see that they are much noisier than the data. But when you go after the aggregation, the noise is significantly reduced. So it means that the image corresponding to the patches that are denoised, they are really not well denoised. Why this thing should work? In the second step, things are very different. This is the error in the noisy patches before the aggregation, and after the aggregation there is a little improvement. But here we have the guide. This is an example how a patch is restored using the so-called MAP, maximum a posteriori, in step 1. You obtain an estimated patch like this, and after the aggregation we obtain something which is very different. This is the original, this is the noisy. At the second step you have something which is very close to the result after the aggregation in step 1, and after the aggregation step in step 2 it is quite close. So there is something that happens in between here. There is an interplay between the first step patch denoising and the aggregation step. Here, let me explain. I mentioned that since when you denoise one patch, it is a group of patches that you denoise. So there are many overlapping patches. In this way, a pixel is estimated many times since it belongs to different groups of neighboring patches. It can be denoised to 20, 100, 500 times. It depends how many times it will appear in a group of patches. But here I follow only one pixel, only one. How it is denoised in each group. This is the value of one pixel when it was denoised in different group patches. And these are 2 pixels in the same patch that I presented in these are 2 pixels from this image, and they go to this patch. How they go, the way they go to this patch is here. You see that there are quite a lot of oscillations, I would say, or outliers, and it is really, this was very surprising. The value is going between some negative values up to 100, here between 10 and 1 to 120. And then when you go up to the aggregation step, the mean of these guys is good. Why it is good? Let me illustrate the aggregation. This is the noisy image. First step, we consider only non-flat areas. The flat areas are in black. And for each patch, only one estimate is presented. Then we aggregate them. You see the difference? This is only the effect of the aggregation. Well, here I wanted to show that the aggregation is mentioned a little bit, just to say a few words. Usually in papers it is not mentioned at all. There is no comments, it is just something that you do. One question that one may ask is, should we avoid negative eigenvalues? It seems not correct to have negative eigenvalues in the covariance matrix. We can try to do this. We can try to put a threshold, theta, threshold equal 1, threshold only the negative filter rate, and if tau is smaller than 0, there is no thresholding. You see that in the first step, if you do thresholding, you have really very good performance in terms of PSNR. Oops, sorry. But after the aggregation, the difference is not so much different. After the second step, for the second step, you see also that thresholding is really not relevant. And in the final result, which is the red curve, the green curve here, you see that thresholding gives better results. We can try to see how this is just an attempt to explain what happens. We want to estimate, for instance, P given from a covariance matrix. We have only the noisy observation Q, we have m sets of noisy samples that are corrupted by Gaussian noise. All samples are, so we assume that they are independent. And we can try to, we know that we have zero mean, we can just try to, oh sorry, to try some VNR estimation in some basis and then to aggregate them. Is there one which is optimal in the posterior mean sense? It seems that yes. We can see that empirically, at least we have some empirical results, that the optimal filter would be given by something like this. But here we have a matrix which depends on the true and the estimated eigenvectors. This is a doubly stochastic matrix, and this is its expectation. We do not know yet how to compute this. Here is, you see that the errors drops really in an important way when we use this matrix F. Another question. What would happen if we set all these coefficients equal to 0? What I mean, sorry, I have to go really. We remove this part from here. Everything we say we give only the mean value. This is removed in the last slide. Only this is kept. And then we aggregate. Based on the mean, estimated mean, we aggregate. The parameter, this is a very noisy image. The parameters, in fact, I have to mention that the parameters of this method were extremely well tuned in order to obtain good results. There are many parameters. It is the patch, they are the patch size, the number of similar patches, which is set to be 3 times the numbers of the pixels in a patch, the search area, the norm according to which this is according to the L2 norm. There is a parameter for the flat areas which is set to 105 and so on. And this is very well optimized in order to work for this algorithm. We use exactly the same setting, but just we put on the right the weights, all the weights are set to 0. It seems still reasonable, which highlights the importance of the aggregation. Here is with a little smaller noise. For smaller noise, it is recommended to use patches 5 by 5. It makes 25 pixels per patch. 3 times 25 makes 75 similar patches. The search area is well fixed, and we use exactly the same setting, and we put only the weights are set to 0. So this is my conclusion. It is very curious to see that from a very poor denoising in the first step, after the aggregation we have very good results. We can try to draw a model for the aggregation step, and there is an interesting interplay between the negative eigenvalues of the empirical covariance matrix. It is not empirical covariance matrix naturally, and we want to better understand this interplay. Thank you.
Thank you very much, Mila. We have time for questions.
So in your experiments, you're using the collaborative version of non-local means, where you denoise all the patches in the cluster.
Yes, yes, yes. It is the same as on the IPOL.
Yeah.
Yes, I have a question on the original method.
Yes.
Which it seems that the difficulty is that there is no constraint on positivity of the covariance estimates.
Yes.
So many people in statistics have been looking at going back to James Stein in the 50s to shrinkage types of approaches as opposed to subtraction approaches.
Yes.
Which always ensure non-negativity.
Yes.
Right? Yes. So would this be a better approach in your opinion?
I already answered this question, but I'm happy to answer it again.
Yes.
Here is thresholding here. In the first step, you see, before the aggregation, there is a significant increase of the PSNR if you threshold negative step eigenvalues. Yes. Significant. After the aggregation, there is still some improvement, but not so much. There is, accept. But at the second step, even for the estimation of the noisy patches, there is no significant difference. And for the aggregation after the second step, the green curve here, you see that it is clearly better if you don't threshold. This is very curious. If you don't threshold, results are better. In fact, the fact to have a first step estimate that is better does not ensure that the second step will be better. Usually, if it is too good, the first one, the second one is not good.
My point is different, though. My point is, don't even start out with a correction of the covariance, which it uses subtraction of the noise term. Instead, start out with a shrinkage estimator, where you don't have any problems in the beginning. So you don't need to even consider threshold in that case. So there's optimal methods. James Stein, also there's a recent work by Raj Nadikaduti on optical shrinkage, optimal shrinkage, that is guaranteed to both preserve positivity,
Yes,
and also to minimize
the risk.
mean squared error, the risk. Yes. So start out with that method.
I did not develop this method. The method is very successful,
Yeah.
and I was trying to understand why it is successful. We have discussed a few times ago that it is better to estimate directly the inverse covariance matrix and so on.
Yes.
I explained what is done in this algorithm, which is a state-of-the-art algorithm.
Any further small questions? Not? I would like to thank Mila again.
Thank you.